It's the 15th and the
Mid-March.
18th.
Mid-March,
March 15th through 17th.
okay.
You know, Tuesday through Thursday.
Yeah, that's,
Wait, we have class on Friday?
Yep, and Monday.
oh,
Because the first time they did that number of years ago, we were told that, yeah, they realized it was a mistake and they would never do it again. And now it seems to be tradition to do it that way.
Wow,
why would they put it in?
I'm not part of that committee.
it does not make any sense.
Scheduling is probably a nightmare. They're probably going, you know what? Screw it, we're just gonna do it anyway. But I don't know.
I will not be able to attend class that Friday, so.
We'll make sure we do something incredible to make you jealous. So master set 19, and then Wednesday 2/23. So if you're looking at the old test for studying, if it says test 1, that is because early on I did a test similar to what I did for 151. I did a test for what would be the equivalent of chapters 18 through 21. And then, recognizing too much material, I broke it down into 2 tests. They are not the first part of test 1 and the second part of test 1 in terms of grades. It's not like they are both tests in full greatness. But it's called test 1A so that it's easier to parallel with old tests. So if it says test 1A, that is the material here. If it says test 1, it'll have some of the stuff from test 1A and some of the stuff from test 1B. Now, because the master set's gonna be handed in on Monday, and the test is 2 days later, the fact that I can get that graded and give you feedback by then, doable, but not likely. So, I will be glad to post the solutions for 19. But that makes a hard deadline for it. If you're running late, if you don't get it by the time I post the solutions, then you basically didn't hand it in. Or, more realistic, I get feedback and I hand it to you right before the test, but I don't know if that will do you any good. Are you okay if I post the solutions and making this basically a hard deadline?
Yeah,
Is there a chance if we handed it in on Friday, that we would get feedback from you over the weekend and be able to look at it on
yes.
Monday? Okay,
I'll agree to that.
okay.
You know, Monday night, or the way it's set up, Monday 11:59 p.m. Solutions posted. So if you're in the habit of getting stuff in a little bit late, please don't be late on this one. All right. Any questions before we start the first material of the second test?
So we have covered everything that will be on the first test.
Yes, I'd like to think so. All right, so basically chapters 18 and 19 are electrostatics. We've dealt with charges that basically are sitting there, just a little bit into the movement as they go from a battery onto a plate, but then they sit on the plates. Now we're going to start getting into electrodynamics. In other words, we're going to get into current flow, not just charge flow, which is what we've talked about. And I've made references to current, but. And I can't remember where I've made if I've made the comments in 252 or 152, so I apologize if this is just too repetitive. I got the positive and negative sides of the battery, which I think we're comfortable with, I hope we're comfortable with. And then I connect it up. That 99% plus of the time, it's the electrons that move, despite what some of you said on the questions from the chapter 18 questions. So electrons are going to flow this way. However, the convention was set up before they even knew about electrons. Electrons were discovered later. It was Benjamin Franklin who set up the precedents with this idea of current flowing downhill. It flows from a high potential to a low potential. And so the convention was set up that current would flow the other way. And by the time they realized there were electrons, it was pretty much set. They said, we're not going to change our conventions. It's just that recognize electrons flow one way, current flows the other way. The symbol for current is a capital I. Actually, that's the symbol for a DC current. In other words, current that flows in one direction. Later on, when we get to AC current, we're going to use a lowercase I, and then we'll talk about the distinction between lowercase I and uppercase I for current. But right now, uppercase I. And what they decided how they decided to define it is it's basically how much charge flows by a particular spot in a particular amount of time. Now I have a delta Q there, which is somewhat misleading because delta is meant change in all this time up until now, and now you're supposed to know. This is amount of current, amount of charge flowing past a particular place. So if I have a wire, well, let's actually take, I have my battery here, I can find the current flowing across this spot right here. But it also, we talked about Kirchhoff's rules. Kirchhoff's current rule. Sometimes referred to as the junction rule. Now specifically for the junction, that whatever current flows into a junction flows out of a junction, or we could also just say whatever current flows into some place flows out of that place. So current in equals current out. And in essence, what this means is I find the current at this spot right here where I put the slash mark, that's actually the current everywhere along the wire. Because current flowing in there is equal to the current flowing out of it, and you can always just trace that back one way or the other. So it's the same current throughout the whole wire. And current flows. I don't know why I keep wanting to drop an R there. I flows from high potential to low potential. But the electrons flow low potential to high potential, because it's a negative charge, so it's going to flow the opposite way. So let's delve into this just a little bit more. Questions before we delve into it a little bit more? So if I have a wire, let's just take a section of that wire and look at it blown up here. So this is a section of wire just blown up. And if you have an electron that's flowing, so let's have the electron flowing this way. So this is the high V and low V. I have electrons that are flowing to the left. Current is flowing to the right. Now some textbooks differentiate and they say, yeah, electrons are flowing the other way. Let's call that the electron current. And the other one, the traditional current. Just so you know, if I say current without any qualifiers, that is the traditional one. Now the electron's just not going to be flowing through. It's not like I have a pipe there, but the electrons are being shot through it. Not in what most of you will experience in your lifetime. At the particle accelerators, you can get that. You just get a pipe and you shoot electrons through it. But the electron is going to come in and it's going to hit stuff. There are atoms throughout this whole thing. A wire is solid through, and so the electron is going to come in, it's going to hit something and bounce, and then hit something else and bounce, and hit something, bounce. The electron basically is moving in the generally to the left, but it's not just cruising right through. The rate at which that electron is actually moving is known as the drift velocity or drift speed. So that's not how fast the electron is actually moving between collisions, that's just how fast an electron tends to be moving in the direction of the electron flow. So a couple definitions here. I'm going to take a section of it like that. The cross-sectional area is A, so A is the cross-sectional area. This distance here is delta x. And delta x is just how far the electron moves on average within a certain amount of time. In other words, it's just the drift speed times whatever time increment I pick. And so I have a volume here. The volume of my cross-section, the part at which I'm looking, is just my cross-sectional area times delta x. So this is the volume of section of interest. Now within this section of interest, I have capital N. I'm going to be doing a lowercase n later. This is a capital N, which is the number of mobile charge carriers flowing through. It's not the number of charges, because all these atoms have a lot of charges there. This is just the stuff that is going to be moving. I'm going to let Q be the charge of a mobile charge carrier. Now I'm going to just stick with generic Q for right now. At some point I'm just going to go, you know what, these are electrons and the charge is a negative E, but I'm not worried about that right now. I'm just going to leave it generic as a Q, and later on I'll change that Q specifically to charge of an electron. So N, lowercase n, is the mobile charge carrier density. In other words, it's how many charges do I have per unit volume. So that's just the number of charges I have per volume. And so therefore, the number of charges I have is just whatever that mobile charge carrier density is times the volume. Not a whole lot of fancy stuff, almost circular in reasoning, but there's just, traditionally, the formula one of the formulas we're going to come up with uses the lowercase n instead of the capital N. Primarily because if I have a wire here, I want to have something that's a little bit more generic than, if I specify capital N, that means I have to specify the volume. And what I really want to do is use the more generic term of, well, what is the mobile charge carrier density at any point? And so the charge that is now flowing through is going to be, well, it's the number of charge carriers times Q, times the charge per carrier over time, which is just Q little n V over time, which is just Q in the cross-sectional area times delta x over T highlighting the substitutions I made. So this capital N here is this, and then volume is this. And delta x divided by the time that we're talking about here is just the drift speed. So this right here is just the, oops, did too much in that, is the drift speed. So I'm left with the charge of whatever's flowing through times the charge carrier density times the cross-sectional area times my drift speed. All right, questions up to here? We're not in a final form yet. This is just we're at the rest area.
So drift speed is V as in velocity with a sub capital D. Is that what you're writing?
Yes, the V as in the symbol we've been using for speed. There's
Right,
no vector
it's
symbol.
not a vector. Right.
Yeah.
Okay.
And V for drift. All right, so Brooke.
Just clarifying, that changed the, what you have squared in blue is the like delta x over t, that's the drift speed?
That I use delta t and t almost interchangeably.
Okay,
Delta x is how far the thing has gone in some time t.
okay. So what's the drift speed?
The drift speed is, well, as I wrote over here, the drift speed would be delta x divided by delta t,
Oh,
and I'm just using t instead of delta t because I'm lazy.
okay, thank you.
Okay. Let's see if we can narrow down that drift speed a little bit better. If the acceleration is constant, we have a nice set of formulas to work with. One of the formulas, what I refer to as cake formulas, is that my velocity here is equal to my initial velocity plus acceleration times time. And if we think about it, when the collision occurs, the collision can occur from any direction. The electron might hit it when it's bouncing back this way, or it might hit something when it's going this way. it's gonna hit something in pretty much any direction, and because of randomness, my average initial speed or velocity is 0. Or you're looking from the point of view that it hits something and it stops and bounces backwards, it has to stop for a moment. What we're concerned about is just after the collision until the next collision occurs. So that, on average, is 0. So now I'm just left with acceleration times time. So an electron's going to hit, and it's basically going to go till it hits something else. So I'm going to define the mean free path time. We use the letter tau, is the time, the average time between collisions for a single charge.
When you say a single charge, do you mean like a single electron?
Yeah, an electron hits something, and then on average, how much time is it before it hits something else? So basically, it's the time under which it's under a constant acceleration. Now the acceleration, well, I know acceleration is force divided by mass. But we're dealing with an electric force acting on a charge, and so that electric force is just Q times the electric field divided by mass. I guess I'm really not worried about direction at the moment here. Yeah, there's a minus sign that shows up that we're hand waving it away. Now the electric field is being created by the fact that I have this potential difference in the battery. The thing that's driving these electrons, we could talk about the reason those electrons move and the fact that they move from low potential to a high potential, or we could look at it from the point of view of the high potential and low potential create an electric field, and the electron moves opposite the direction of the electric field. So if I've got a battery here, again with high V and low